Hello everyone, and welcome to the finale of Assignment 1 of CIV 398. So, this last question, question 6, it's great for you guys. It's a bonus question, but luckily for you guys, it's actually pretty easy because it deals with orthonormal basis. And there's basically two properties of an orthonormal basis, which we'll discuss, but because of those properties, it makes the questions actually pretty easy. So the question itself says, consider the orthonormal basis set B, which is composed of basis vectors e1, e2, and e3. If the vectors u, which is equal to 2, 1, and negative 1, as well as v, which is equal to 1, 3, and 5, are aligned in the directions of e1 and e2 respectively, determine the orthonormal basis vectors e1, e2, and e3. So to do this, what we're going to do is we're going to utilize the properties of an orthonormal basis. And there's two big properties that you guys are going to need to know, which will help us solve the question. The first one is all the vectors in an orthonormal basis are perpendicular to each other. So if we were to dot any of the two vectors, it should be equal to 0. The reason why? Well, if they're perpendicular, cosine of 90 degrees is 0. Our dot product will be 0. And this doesn't just go for E1 and E2. If we're working in R3 and we have an E3, then E1 dot E3 will also be 0, E2 dot E3 will be 0, and so on. The second property that you're going to have to remember is that these vectors in an orthonormal basis have a unit norm. So the norm of all those vectors are equal to 1. So again, if we're working in E3, we'll also have the norm of E3 is equal to 1. So a lot of you guys may be wondering, well, what exactly does this look like? And I'm going to show you the two cases that our brains can handle, which is 2 and 3D. I have no idea what 4D looks like. That's a question for Dr. Deeb, not me. So looking at the 2D case, the best way to think of it is kind of looks like an XY plane. Because if you think of a standard XY plane when you guys are graphing all the way even in high school, we had a y-axis and an x-axis, and they were perpendicular to each other. So it's kind of the same looking thing here where E1 and E3 are kind of like the x and y axis because they're perpendicular to each other. We can extend this into R3 by adding that E3 vector. And again, referring back to the math you guys already know, this looks pretty much like the standard x, y, z coordinate system that we always use. And this is why orthonormal bases are so important because they're actually very standard. And again, the last thing that we're going to always have to remember is that the norm of these, or the lengths of these vectors, are always equal to 1. So using those two properties, we can actually solve this question very easily. So let's look at the question and try and apply some of these properties. So looking at E1 and E2, the problem actually says that the vectors u and v are aligned with E1 and E2 respectively. So we're going to have something like this, where we have u in the same direction as E1 and v as the same direction as E2. And this is really, really nice because remember, E1 and E2 must be perpendicular to each other. So because of this, we can conclude that the vectors u and v are also perpendicular to each other. So they already meet one of the two criteria to be an orthonormal basis vector. The problem with them, however, is the vectors do not have a unit norm. And that's very easily proven because if we go referring to u, sorry, if we were to go 2 squared plus 1 squared plus 1 squared and then square root it, well, we're not going to have, a norm of 1. So the only thing we actually have to do in this case is normalize these two vectors because, again, they're already perpendicular to each other. And normalizing vectors, very simple. You guys actually learned all the time in Eng 130, think of the unit vectors. And all we do is we take the vector itself and we divide each one of those components by the norm of the vector. So in this case, if E1 is aligned with u, then E1 is equal to u divided by the norm of u. And then E2 is equal to v divided by the norm of v. So just right then and there, we already have 2 out of the 3 components. That's why I said this bonus question is actually pretty nice. Not a lot of work involved, and hopefully you guys can get some easy marks. I'm not sure if these are worth extra marks or not, but that'll be a question for Dr. Sammer. So the question becomes, okay, well, we have E1 and E2, but how do we get that third vector? Because the question was very nice in that it related vectors u and v to the basis vectors E1 and E2. So now we're going to have to look at the second property, or I guess the first property I listed, and that is the vectors in an orthonormal basis set are all perpendicular to each other. And recall that if we have two vectors, we can attain a third orthogonal vector, which is the same as perpendicular, using the cross product. So if we cross u and v, we're actually given a vector that's perpendicular to u and v, and we'll call this vector w. And this w, since it's perpendicular to u and v, and in turns e1 and e2, this vector will have the same direction as e3, which is exactly what we're wanting. So we have two options in this scenario. The first is kind of the most trivial, which I think a lot of the students will do, and that is we're going to cross u and v together to obtain w. But remember, since u and v are not normalized, we'll then have to normalize w to transform it from w into e3. However, there's a little trick here to save you guys some time if you guys want to save time. Which I'm sure you guys are third years. I'm used to teaching the Edge 130 kids, and I always tell them save time by doing any trick you can, because time is your best friend in a midterm. It's usually not you guys being able to know the material, it's how fast you guys can spit it out onto the paper. And the same goes for this class, of course. So any trick you guys can do to save time, always take it. And this is, instead of crossing u and v, recall that we already have e1 and e2 from the previous slide. So if we have e1 and e2, we can cross them together to obtain e3 directly. Because a little trick is the cross product of two norm vectors, in this case e1 and e2, results in a norm vector. So if we cross e1 and e2, our resultant vector will already be normalized. And since it's in the direction of e3 and normalized, well, that vector will be e3. So there you have it. There's how to get e1, e2, and e3. Although it's a bonus question, probably not too bad. I expect a lot of you guys to get it right off the bat. So thank you guys so much for listening. Thank you guys so much for listening to all the videos for assignment 1. I guess this concludes assignment 1. And I will see you guys in assignment 2.